Let's now consider the consequences of these Hamiltonians having exactly the same structure in either representation. To do that, let's consider now the corresponding time-independent Schrodinger equations that we're getting, but written down in the natural units that we've just derived. So when we look, for instance, in the real space representation, my Hamiltonian is minus 1/2 two derivatives plus 1/2 x squared, multiplying the function. So it's going to be minus 1/2, no more constants anymore, two derivatives of my real space wave function, plus then 1/2 x squared times my function, right? Is going to then equal, and this is of course a function of x, this is a function of x, will just equal the energy multiplying my function of x back again. Now, these are bound states, so they carry a discrete label n that I can attach to them like so. In the momentum representation, it's the same thing again. That's the whole point here. I've got minus 1/2 of two derivatives, so it'll be minus 1/2 two derivatives of phi tilde now, which is a function of k. But again, these are bound states, so they will have a discrete index, plus 1/2 the variable squared, 1/2 k squared, phi tilde of n of k, will equal then en times phi tilde n, which again is a function of k. Now, look at these equations. They are absolutely identical to one another. The only difference is that I happen to have written this equation with x's in it and this equation as k's in it. But other than that, they are the same exact equation. They therefore have the same exact solutions. And the other interesting thing is that because we are in 1D, right? D equals one dimension, right? There is only one solution for each En. Of course, up to a normalization constant, right? We don't know what the normalization constant might be, but they are identical up to that normalization constant.